Hello everyone. Let me know if the screen is visible and if you can hear me. Anyone? Hello. Yeah, fine. So we'll wait for 5 more minutes and see if any more of you will join. Then we'll start. By the way, some of you were interested last week whether you will be getting the recorded lectures or the notes, right? So let me just share the link in the chat box. So the first link is the video lectures. It will be uploaded in this web page. And the second one is the Google Drive link, which is in you can view and download the documents, right? If you are interested, you can simply follow these two links. It's available in the chat box. So let me just start. I think people will join and they can follow. So this is just to make sure you are joining the right course. It is NOC EE-62. This is the tutorial session for basic electronics course. The course instructor is Professor Mahesh B. Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. So this is the second week and we go live every week 3 to 5. So there are certain prerequisites which I mentioned in my last session also. So I would request you to keep this in mind. The one thing would be you should have attended the previous week lectures, right? Then only it will serve the purpose. Another thing will be that you should have attended the assignment problems by yourself at least once. Then that will be good actually. So you can discuss your doubts and all, right? And please be muted during the session. If you have any query, you can raise hand or after the question or the particular problem is discussed, then you can unmute yourself and ask the doubt. It will help in smoothly conducting the session. And also at the end of 2 hour, as I mentioned, it is a 2 hour session. So around 4:45 or 4:50, I will allow everybody to ask their generic doubts for 10 minutes. And please keep a scientific calculator along with yourself if you want to follow this. It will be very helpful. So this is week 2. Last week we have touched upon this superposition. Second. Last week we have touched upon this superposition theorem, right? Superposition theorem, then Thevenin theorem, maximum power transfer, and some more circuit techniques, right? Some more, rather say, network theorems. This mostly consisted of the resistances and this control sources and independent sources, right? This week, what I am planning is to move to the memory-based elements, right? As you know, that memory-based elements are these capacitances and inductors, right? Because they store energy in forms of charges. So before dealing with this first problem, this is a transient analysis of a RC circuit, first order RC circuit. Let me just brief you what this is about. So C and L, right? Capacitances, I am denoting as C and L as inductors. These are memory elements. Now, what do I mean by memory elements? Memory elements means, you know that human memory can store information, right? So capacitances and inductance also are used as a storage device, or it stores information in terms of energy, energy, say for C, it stores charges, electrical energy, and inductors it store magnetic flux, right? In terms of magnetic energy. All the memory devices you see these days, right? They are used to store this information or data. Capacitances are the basic building blocks, or would say that capacitances play a very vital role to store their states, right? So these are very important elements. So as you can see, if you store some memory, so it should be time dependent, right? Till this time, how much information and what are the states the capacitances have been. These are time dependent elements, and their characteristics are governed by differential equation, or rather I should say the dynamics of these systems governed by differential equation. Now, this is so far so good. Now just let us see if I have a voltage source, right? Let make it time varying. And I have two resistors, R2, R1, this is V source, it is time varying. Then what would be the voltage at this point? VR2T. VR2T will be this, it is a simple voltage division, right? So it has no issue. Now tell me What if I tell you to find this? What would be the voltage across this? So how can you tell that what will be the voltage across this for any arbitrary time varying input, right? It's not so trivial actually. It can be done, but difficult. So we'll first take the case of a constant voltage source. Say VST is equal to Vs, which is constant, and see how the circuit behaves, right? So what I am interested in, this is a DC source and how my Vc will vary over time, right? So to analyze this, first let's consider my Vs to be 0. As I have said last week that voltage source 0 means it's a short circuit, right? So your circuit is like this now. This is your Vc T. So we want to write the dynamics of this circuit, and that can be done by writing a differential equation. So how does the differential equation come? First you need to understand that. So for the time being, let's say current is flowing, right? I. This current will be current will be consistent through R and C because it's a series combination, right? So if you see, and this voltage drop, let me say VR, right? Let me say this is VR. Then I can, using KVL, I can write VR plus VC of t is equal to 0 through this loop, right? Across this loop, if I write KVL, then I get this. So your VR, the drop across resistance is your I times R plus your VC of t is 0, right? What is I? What governs I current here, right? The current is across a capacitance if there is a voltage VC and a current is flowing I. Note the direction of the current, right? This IT would be C dVc t of dt. How does this come about? Your I is dq of dt, right? Q is charge here. And your charge across capacitance you can write as C into V. For our case, it is Vc, right? And if you take your C constant, then it becomes dVc dt, right? So in this case, I can simply substitute I as C dVc dt plus your Vc is 0. So if you solve this first order differential equation, what do you get? You get the solution as Vc of t as Vc at 0 e raised to minus t by Rc. Is this okay? How this solution come across? Anyone? From this step to this step, how does it come? Everybody is clear about that? You can unmute and speak up.
Yes,
Okay,
sir.
fine. Then I'll move on from this point. So you see, if I plot the voltage across capacitor, right? This voltage across capacitor, how does the profile looks like, the voltage profile with respect to time? So at t equals to 0, if you put in this equation, VCT is nothing but your initial voltage, right? VC0. So it will be somewhere here, VC0. And then it decreases exponentially. And at t tends to infinity, my VC of t tends to 0, right? So this capacitor is discharging, and at infinity it reaches 0. So now tell me, when t is equal to RC, what is my VCT? My VCT would be nothing but VC0 into e raised to minus 1, or VC0 divided by E, right? So, and let me call this tau. This tau equals to RC. My VC of tau is nothing but VC0 by epsilon, right? Similarly, if you want to plot the current across the capacitance, then it will be just what is your current across capacitance? It is nothing but your C dV dt, right? C dV C dt. So if you take derivative of this equation, you get it. What do you get? You get minus of Vc0 by R. C and C will get cancelled, and it will be e raised to minus t by RC. So if you want to plot your current, it will start from some negative value minus Vc of 0 by R, and then eventually it reaches to 0 at infinity, right? So why this negative sign is coming? Because we have taken the convention that current is, if you can see, this current is positive when coming into the positive terminal, right? And we have calculated taken current as going out of the terminal. That's why this negative sign convention is there. So this is how the circuit behaves when there is no external voltage source is applied, right? Now what if hold on. Now what if I apply a constant voltage source? This tau is, by the way, called the time constant of the circuit. Time constant of the circuit. It is nothing but a characteristic time which determines how much sluggish your system is, right? How much delay, how I should say, how sluggish your circuit is. If you give any input, what time it takes to reach the steady state, right? By the way, the steady state is a term, right, which will be new to you. So this tau is your time constant. Now let us say you take 5 tau, right? And each time, now suppose I take 2 tau, it will get 1 over E of this value, right? So after 5 tau, it becomes almost negligible, right? So what we say that generally around 4 to 5 tau, beyond this we can consider our steady state condition. Means the circuit has been settled. This steady state is actually, if you want to go proper theoretically, so you should take infinite time, right? But that is not feasible. So what we are interested is how the circuit behaves beyond 5 tau or inside the 5 tau time, right? And this is your, what you say, transient state, means how your circuit is behaving, right? So Now if I move on to this is my Vs. So now if I take my I in this direction and this is my Vc of t, again using KVL I can write simply Vs minus voltage drop across resistance minus Vc of t is 0. Then how do we go about it? Vs same way, C dVc dt R V minus Vc of t equal to 0, and then we have this Vc dVc of t dt plus Vc of t minus Vs by Rc equal to 0, right? And if you solve this differential equation, you will get your Vc of t as your Vs. Here I am assuming that Vc of 0 is 0. Then you will have 1 minus e raised to minus t by Rc. This is how your voltage across capacitance will look like, right? Initially it starts at 0, t equal to 0, it will be 0, and then it reaches to at t equal to 0, Vct is simply 0 because this term will be 1, and at t tends to infinity, my Vct, or at steady state it is Vs, right? Simply because my capacitor is being charged, right? So your profile would be something like this. This is your Vs, this is your 0, right? And how will the current behave? Similarly, you can just compute current in this case, C dVct of dt, and you will find that your current is C, and then you have your Vs into e to the power minus t by Rc, C, and you just differentiate this, and you have Rc, right? Then you have Vs by R e raised to minus t by Rc. That means, let me add one more page. You will see your current behave like your current will start from this and it will decay like this. This is your Vs by R. Now, how intuitively you can tell from this figure? See, at initially it is 0, right? That means it is your short initially. Then what should be the current at t equal to 0? It is just Vs by R, right? Then as the capacitor is getting charged, then my current gets decreasing, right? And it reaches 0 at steady state. So this is the response of a first order circuit, right? This is the response of a first order circuit. Now let me tell you what do we mean by order of a circuit, right? It's very important. Please focus on this point. Order of a circuit. How can you determine? One way is you write the differential equation and check the order of the equation. But sometimes there will be so many elements that you cannot just write every differential equation, right? So you need to go intuitive about it. So that approach is you see how many independent storage elements are there. Independent storage elements. That means C and L. Please note this term carefully, independent. What do we mean about it? Let us see it through some examples, right? If I ask you to tell me the order of this circuit, what would be it? Anyone? You can unmute and okay, using chat box, fine. It is one, right? Rightly said, it is one. Then tell me what is the order of this circuit? What is the order of this circuit?
1.
Why do you say that?
Sir, you can combine both the capacitors,
Okay, you're
right,
right.
to effective
Order is one,
capacitance.
right? Now tell me what is the order of this circuit? What is the order of this contraption? C2, C1. What is the order here?
2, sir.
Okay, you are using the same logic, right? You cannot combine the capacitances here. Now tell me what is the order of this circuit? What is the order of this circuit? Anyone?
Probably 2 only, sir.
Why do you say that?
Sir, it's 1, sir, because I guess the same current is passing through the both the capacitors.
Why the same current is passing through the both the capacitor? It is not right. There will be current flowing through this element, and the sum of current will flow this, right? The current is not same. But you are right that the order is one here. How do you prove it, right? One way is just write the differential equation, write the diff equation, and check and satisfy yourself that it is first order circuit. Or you can simply check that, at order of the circuit does not depend upon what is the frequency of your input, right? Now, what is the impedance of a capacitance? 1 over j omega c, right? If I use a 2 pi f into c, suppose I use f equal to 1 gigahertz, then my zc is almost equivalent to 0, right? So you see, if I have a voltage source here, a sinusoidal voltage source whose frequency is very high, you can simply assume that this capacitance, most of the current will flow through this capacitance than this resistance, right? So it is becoming equivalently a series combination of capacitances. You can simply ignore R in that case because current will choose the least resistive path, right? So in that way you can tell, and also you can see that the node voltages are dependent, right? Of this node A, B, and C. This is the intuitive way. So this you have to practice some, you come up with more contraption and combination of the circuits and you try it out how much what is the order of the circuit, right? You do it like you solve the differential equation and then also you check it intuitively. So after certain repetition, more practice, you will get to know how to intuitively tell the order of the circuit, right? So this is one case. So this thing you can take it as a homework. Yes.
Sir, this explanation for high frequency. If low frequency, then
No. What I am telling that in low frequency also, see, your order of the circuit does not depend upon the frequency of operation, right? I am telling you how to intuitively think that how you can tell this is a first order circuit. For the sake of it, just let me solve this, okay? Just assume that this voltage is Vs and this is Vc2, this is Vc1, right? Then what is the voltage relation? If you take the outer loop, it is Vs minus Vc1 minus Vc2 is equal to 0, right? One condition you are getting this. And if you take node B and use KCL there, you see current through resistance Vs minus Vc2 by R plus current through C1, that is C1 dVc1 by dt, right? And that should be equal to current through C2, right? C2 dVc2 dt. Okay, now you substitute dVc2 dt equals to your d dt of Vc2, right? Vs minus Vc1 by R. Vs minus V1 from this equation. Then your dVc2 becomes, this is for you, as you have said, let me take it low frequency. What is the lowest frequency possible? That is 0, right? Let me take, it is not at all, it is a DC. That means it is not time varying, right? So it would be 0, so this would be dVc1 by dt. Now substitute this back to this equation. We get Vs minus Vc2 by R plus C1 dVc1 dt equals to C2 to be minus dVc1 by dt. So what do you see? dVc1 by dt into C1 plus C2 plus Vs minus Vc2 by R equal to 0. What is the order of this equation? This is 1, right? So this way you can check, right? What I was telling is how to intuitively, by seeing the circuit, you can tell what is the order of the circuit, right? So order is fine. So I think you are convinced that the order is 1 here for this contraption. So you can try out few more examples, right? You make your circuit by yourself and then check it by intuition and your differential equation, right? Now one more thing before I go to the problem section. Just tell me, does capacitor block DC? You might have heard this term, this statement, right? Anyone? What we get by knowing order of the circuit? By knowing order of the circuit, you get how
Frequency of DC
much?
0. Frequency of DC equal to 0, sir.
Sorry.
Frequency of DC equal to 0. So
Mm-hmm.
it is
Frequency
so
of
the
DC is 0, so you are telling that it is the impedance is infinity, right?
yes, sir.
So
Yes, sir.
capacitor is blocking DC, right?
Yes, sir.
Okay. So just let me do this. If you put this is your, suppose this is your Vs, right? This is your Vs, this is T. At T equal to 0 is you switch on the power supply. What would be your Vc? What would be your Vc from the last discussion? Can anyone tell how the plot will look like? See, earlier case we had a R here, right? Exponential increase to a steady state. Okay, let's see. Earlier we had a R here, right? Now we have R is 0. So what is your time constant?
0.
Time constant is 0, right? So if your time constant is 0, that means it responds immediately. It immediately follows the input, right? You do not have what if your time constant is not 0? If your time constant is not 0, then it will be it will be an exponential increase. Abhishek Kulkarni, right? You understand please this carefully, that if your time constant is 0, that means to get Vc by E or any value, it takes no time. It takes 0 second, right? So it just simply follows the capacitance. Capacitance voltage follows the source voltage, right? What does that mean? That means if this is your Vc and if your Vc is equal to Vs instantly, then the situation becomes simply two voltage sources of the same value, right? Then what is the current flowing in this branch? Current is 0, right? That is, current is 0 means this capacitance which is effectively blocking my DC, right? It is blocking my DC. So capacitance does block DC. Now tell me one thing. What if I just change it with a current source? DC current source, right? How will my VC look like? Anyone? Uh, but initially before charging, capacitor allows DC. Initially before charging, capacitor allows DC. I am not getting. Anag, can you please? T less than 0, capacitor allows DC. How? Why do you say that? Can you please unmute yourself and speak up? It is not charged, right? Charge to supply voltage. I am not getting you. Probably you can unmute yourself and speak up. That will be a better option.
Sir,
Yeah, Anand.
actually, yes. Before charging, it is going to allow DC, right? Since it is not charged to the supply voltage,
Before, no,
capacitor voltage.
see, it is instantly charging, right? Your R is 0.
Oh, R
So
is
it is
0.
it is following your input voltage at every point, every instant of time. So at every instant of time, your current will be 0, right?
Yes. If R is
So
present, then it allows DC.
yes, yes. No, no, it is not allowing DC. That is a different thing. If R is present, it is allowing to charge the capacitance. That is time varying, right? IT.
Yes,
Your
irrespective
DC
of
is the,
AC or DC.
so that means when you have Rx 0, your time constant is 0. That means there is no current. Now tell me what happens if I replace the voltage source with a ideal current source? How should the voltage profile look like? It is just a simple integration, right? Your IC is C dVC dt, right? So your VC will be simply IC IS, right? IS by C into T. So it is increasing, right? It will never go to steady state. So what is the time constant from this discussion? Can you tell me what is the time constant here? Anyone? What is the time constant for this circuit? This is the same thing as this. Who is that? Gunjan. Yes, you are absolutely right. The time constant is infinity, right? Because you see, when you remove this or you null this current source, you see a resistance, right? R is infinity. So your time constant becomes infinity. So keep in mind that capacitor blocks DC. It's not absolutely correct statement. Capacitor does not allow to pass current through it if it reaches the steady state. But in this case, it is never reaching the steady state. As time increases, it keeps going on and on, right? So let's move to the problem now. So this was the problem. Let me copy it. So they have asked that in this circuit shown, the capacitor voltage initially is 0. That is a important point. That is an important point. What is the time constant of the circuit, right? How do you find the time constant of the circuit? We have analyzed the circuit for a single voltage source, a resistance, and a capacitance, right? This we have analyzed. Can you convert this circuit to this configuration? And how do you convert this? Anyone? I see someone is Anag is telling RTH. That means Thevenize the circuit, right? You just take the Thevenin configuration, Thevenin theorem. You use Thevenin theorem to convert it to this series contraption of a voltage source and a resistance, right? So how do you find your RTH? Quickly tell me what is RTH. RTH would be you null this source. That means this becomes a short, right? So your R1 is parallel to R2. That is 3 cross 5 by 8 is your 15 by 8 kilo ohm, right? And what is your this C? C is your 4 microfarad. So what would be your time constant? It will be RTH into C. That means 15 by 8 into 4. This is C, this is kilo ohm. So sorry, this is micro, this is kilo. That means you have a 10 raised to minus 3 term. So it will be 7.5 millisecond. So the right answer is D, right? This was pretty easy. So move on to next problem. It is the same circuit. They want us to find what is IC 0 plus 1, right? At t equal to 0 plus 1. 0 plus 1 means at this instant. That means your voltage is 5 volt here, right? At 0 plus 1, what is IC naught? So at t equal to 0 plus 1, equivalent circuit becomes, you have this, and what is your C here? What is your VC? VC at 0 minus was 0 volt, right? in question number 1. So VC of 0 plus will be VC of 0 plus will be 0. Why do you say that? Who is this? Gunjan. Can you please unmute yourself and explain why do you think it is 0?
Capacitor voltage can't increase instantaneously.
Why?
Uh, Sir, rate of change of voltage, it oppose uh, that.
But we have seen this, right? We have seen that as input is changing here, your capacitance voltage is also changing instantaneously. So what is the fundamental behind it? When it will not change?
Hmm.
You can simply see, right? We have just explained that when there is a R delay, RC delay, if
Okay.
your R is
Yes.
0, then your
Hmm.
capacitance voltage can change, right? If your R is 0 instantaneously. The delay is causing, this is called a delay element, right? This delay is being caused by the presence of R and C both, right?
Okay, sir. Got it.
So in this case, as you have rightly said, we have resistive or damping element in this circuit. So your VC plus will be 0. That means I can simply just short this circuit, right? This is your 3K, this is your 5K, this is your VS, right? And what was VS, by the way? VS, VS is mentioned. Okay. What was your VS? I guess your VS is, this is not mentioned, right? Let us take it as 5 volt. Okay. If this is your 5 volt, then what is the current? This branch is not present because there is a low impedance path. So all current will flow to this. So your IC is basically this IC 0 plus. So your IC 0 plus will be simply 5 by 3, right? Milliampere. And that is your 1.67 milliampere, right? So your A will be the right option. Then moving on to the next question. In this circuit, what is VC infinity? So VC infinity, right? We have seen that C at steady state behaves as open circuit, right? Why open circuit? Again, I am referring back to our discussion. At steady state, this will be whatever the charge will be there, your I will be 0, right? Why did we do that? Here, your I will be 0. So any circuit, any element through which if your I is 0, that refers to a open circuit, right? So capacitor at steady state behaves as an open circuit. So in this case, if capacitor is open circuited, then my at t tends to infinity, equivalent circuit becomes this voltage source, this, and a open circuit. So your VC is nothing but the potential across these two nodes, right? This is R1, R2, this is 5 volt, 3K, 5K. So your VC infinity would be nothing but 5 by 8 into 5 volt. that is 3.125 volt, right? So your answer would be, let us see, B. So I think there are no questions till this point. So moving on to item number 4. What is I1 at 15 millisecond, right? If such a problem is given to you, what is the first step you should check? You should check how your timestamp, means t equal to 15 millisecond, whether it is falling in your transient region or it is falling in your steady state region, right? How to check that? We need to check that how t is with respect to my 4t or 5t. Let us take 5t. So what was your tau? Your tau was 7.5 millisecond, right? We can easily see that t is here 15 millisecond or equal to 2 tau, that is less than 5 tau. So it is in my transient region. So I cannot simply open circuit the capacitance. That is the takeaway, right? I need to calculate the voltage because this is only my time varying element here. So VC, what is the first step is that VC of 15 millisecond. What is that? How do we do that? I have already told you the formula, right? Where did you do? Here. This is the formula, right? This is the formula. To calculate it at any time instant, right? So if we calculate VC, say Vs 1 minus e raised to, no, let's say not Vs, let's say V 1 minus e raised to t by Rc, right? This Rc, you know, this Rc is nothing but this. What is your V here? In the expression we have derived earlier, right? The circuit was this. So you need to consider V as VTH. So what was your VTH? Did you calculate that? What was your VTH? No, you did not calculate, right? So your VTH here would be how much? VTH would be simply 5 by 8 into 5 volt, right? That is your 25 by 8 volt. That is your 3.12. Oh, I think we have calculated that. Here, this one, right? 3.125. So this is your 3.125 VC of t, or VC of t equal to 15 millisecond. 3.125, 1 minus e raised to minus t is 15, RC is 7.5. So your VC would be how much? Let me calculate it quickly. 7.5 e raised to minus answer 1 minus answer into 3.125. It is coming 2.7 volt, right? So now your equivalent circuit, at t equal to 15 millisecond becomes, this is a voltage source, this is a resistance, and this is a voltage source, right? This is just 2.7 volt. For the simplicity, let us replace the capacitance with the stored voltage, right? What is the voltage across it at that instant t equal to 15? Remember, it is changing at every instant, right? We are checking it at t equal to 15 millisecond. this circuit is valid only for t equal to 15 millisecond. So this is your 3K, this is your 5 volt, this is your 5K. So they have asked us to find this current I1, right? So your I1 will be simply 5 and this node potential is same as 2.7 divided by 3, right? So 2.3 divided by 3 milliampere. That comes out to be 2.3 by 3, 0.77 milliampere, right? That means your D is the right answer. So let us move to next question. It is almost similar, just a more trickier way to represent the switching, right? So what they have told us, the switch in the figure has been open for a long time, okay, and the closes if the switch is open for a long time, right? That means your circuit was for minus infinity less than t less than 0 minus, your circuit was this and this was a open. Now can you tell me what is the VC, what is VC not minus? Anyone? TK 5 microfarad. What is my VC not minus? Why it is 0? This came from Anag, right? Anag, why it is 0? You can unmute and speak up. Okay, switch open, but why it is 0? You can unmute and we can have a conversation. No, not charged. Okay, please tell me.
Yeah, since it is not charged, switch is open.
No, suppose your switch is open, right? And let me tell that this VC minus infinity was something 5 volt. Let me tell you that. So what would be this?
5 volts.
Why it will be 5 volt? There is the catch, right? That's why I have asked this question. See, this is as soon as you consider the switch is open, these are two different circuits, right? You agree?
Yes. Yes.
If this is so, and if there were some charges, there were some initial voltage at minus t equal to minus infinity, then what should at t equal to minus infinity to t equal to 0, would not this capacitor be discharged?
Yes.
Why?
Through the resistor.
Yes, you are absolutely right. Now through the resistor it should have discharged, right? So
Yes.
it does not matter whether it was charged initially at t equal to minus infinity or not, right? Because we have allowed it to relax for a in sufficiently long time, so I can take this value as 0 volt, right?
Okay. Yes.
The concept is here that this has been discharged through this R3, okay? So my VC0 minus is 0, right? So they have asked us what is the time constant of the circuit for this. Okay, so let me draw for t greater than 0, t greater than 0 plus. Let me say if there is a switch, that means there is a step function, right? So then my circuit becomes this, this, this resistance, this capacitance, this 2K, this is 3K, this is 2K, this is 10 volt, this is 5 microfarad. So I need to find out the R equivalent or R Thevenin, right? between these two nodes. Between these two nodes, what it will be? We have to just null this source and then take consideration this parallel to this parallel to this. So RTH would be my 3 kilo ohm parallel to 2 kilo ohm parallel to 2 kilo ohm, right? So this is 1 kilo ohm. So 1 parallel 3, that will be your 3 by 4 kilo ohm, right? Means your 0.75 kilo ohm. So what is your time constant at t greater than 0? Means this circuit is your C into RTH is 0.75 into 5 millisecond. That is your, this becomes 150, 300, 3.75 millisecond, right? The right answer would be C. So moving on to the next question. In the circuit of Q5, what is VC infinity? Okay, VC infinity means we see this contraption, right? We see this contraption. This is t greater than 0. So at VC equals to infinity, what happens? This, let me just draw it in this way, and this is the capacitance, right? This is my 2K, this is 3K, this is 5 microfarad, this is 2K, this is 10 volt. At infinity, my this is open circuited, so this becomes open, and this is my VC infinity, right? So VC infinity would be potential of this. So what is my VC infinity? You can just calculate that. VC infinity would be the 3 parallel to, how much is that? 6 by 5, 1.2, 1.2K divided by 3.2K into 10 volt, 1.2, 3.2 into 10. That is your 3.75 volt, right? So this is your right answer. I think there should not be any problem in this question. So let's move to question number 7. Question number 7 asks that what is VC at 8 millisecond? Again, the same kind of problem. What is the first step? First step is to check. Anyone? What is the first step?
Less than 5T or not.
Yes, right. In which region? In the transient or steady state? In which region will lie, right? Your t is here 8 millisecond. And what was a tau? What did we find? Did we find tau? We find tau 3.75 millisecond, right? 3.75 millisecond. We can clearly see that t is less than 5 tau. So we are in transient regime. So again, we need to use the formula for VC 8 millisecond would be our VTH 1 minus e raised to minus t by RC, the time constant. Your VTH, did we find? No, we found RTH, right? Your VTH would be, oh, this is the same thing. This is your VTH only. So 3.75, 1 minus e raised to minus 8 over 3.75, right? If we calculate it, 8, 3.75 raised to minus answer 1 minus answer 3.75. It is around 3.30 volt, right? So this would be your right answer. So this you are comfortable by now, right? This formula. We just do the circuit, we convert it to we Theveninize the circuit. Because why do we Theveninize the circuit? Because we know the answer for a first order RC circuit. That means the single resistance first order RC circuit, a voltage source, a single resistance, and a capacitance in series. That result we know. So we use Thevenin theorem to convert the complicated network to a similar kind of network, and we use that formula, right? So that is problem number 7. Problem number 8. Problem number 8 is asked what is I2 at t equal to 6 millisecond. Again the same thing. First thing you need to find out what is Vc of 6, right? Your Vc of 6 millisecond will be your Vth 1 minus e raised to minus t by Rc. Vth 1 minus e raised to minus 6 by 3.75. This is your 3.75, 1 minus 6 by 3.75. This comes out to be 3.75 raised to minus 7 minus 7 into 3.75. This is coming around 2.99 volt, or you can just simply take it 3 volt. So now the equivalent circuit, you draw the equivalent circuit, right? This this is a voltage source equivalently, and you use this is 2k, 3k, 2k, 10 volt, and this is your 3 volt, right? What they have asked us to find this current, right? I2. So the same in between same node, it is 3 volt, so this is also 3 volt. That means your I2 is 3 volt by 3 kilo ohm. That means 1 milliampere, right? So A will be the right option. Now this, let's move to next problem. Inductors, right? Wait. So in the similar way, first let me introduce to you the inductors, right? Okay. Okay. Suppose RL circuit. Suppose you have a current source, you have a resistance, and you have a inductor. This is R, this is IS, this is L. Does it matter if I use a current source or a voltage source? Anyone? In this circuit, does it matter if I use this or this? Anyone please answer? No, right? Why not? No, right? Both are same, but why? Yeah, I think you got the point, right? It is just nothing but a source transformation. The same thing, what is the same difference between Norton circuit and Thevenin equivalent circuit, right? It's the same thing. So it does not matter actually. But the ease of for the ease of calculation, I am just taking this one, right? So now let us use KCL at this node A, right? Node A, let us use KCL. So IS is the input current, and let us tell this is, let us VA or node voltage. IS is then VA by R is one current component, and another one is current through this inductor. Let us say this is IL. Okay, so what is the voltage across inductor? The same voltage will appear across inductor. It is nothing but L di dt, right? So this equation becomes plus IL minus IS by L by R equal to 0. Does it look familiar to you? Does this equation look familiar to you? We have just seen this, right, in the case of capacitance. There the equation was dVc dt plus, what was that? Vc minus Vs by Rc equal to 0. These are the same equation, just change of variables and constants, so we can simply use the same result as we get there. So this solution will be IL of t would be your IL of t would be nothing but IS, assuming IL of 0 is 0, right? So it would be IL 1 minus t by, there is RC was there, now it will be L by R equal to 0, right? This equation will be very handy in analyzing the circuits. So what is my time constant for RL circuit? It is nothing but L by R. Okay, and you can easily check the how the currents and voltages are varying, right? This how your IL will vary, IL will vary, will charge up to this. This is your IS, this is 0, right? At certain point, tau equals to L by R, you have IS 1 minus 1 by E. Similarly, you can plot voltage across across the inductor also in the same fashion as we have done in case of the series RC circuit, right? So we'll be using this formula and this formula for the next problem, hopefully. Let's see. So they have mentioned that the switch in the figure has been in position 1, means this and this are connected, A and B, for a long time, and changes to position 2. That means A and C connected, B is not okay. At t equal to 0.3 millisecond, the switch changes back to position from position 2 to 1. What is the time constant for the circuit for this duration? Okay, first let us first simplify our issue and take the cases, right? But one case is this, right? This is the connection. This circuit is isolated. This is your L 1 millihenry, 5 ohm. Yes, R2 10 ohm, 10 ohm, 5 ampere, right? So this is your A, this is C, this is B. This is for minus infinity to for a long time, right? T less than 0 minus. Okay. And another combination is this A and C connected. This is there is a resistance, there is an inductor, and there is this, and there is this, which is not connected, right? 10 ohm, 5 ampere, 1 millihenry, 10 ohm, 5 ohm, right? So this is for what is the timestamp they are telling? 0 plus less than t less than 0.3 millisecond minus. Okay, and then again the switch changes back to position 2 to position 1. That means and 0.3 millisecond plus less than t less than infinity. Is this clear? The timestamps. I think it should be right. There is nothing complicated about it. So this is when we'll use this circuit we'll use for this duration, this timestamp. This circuit we'll use for this duration. Right now, just let me add a page. Okay. So what is that? The question is, what is the time constant of the circuit for this, right? So we'll be using this combination. So can anyone quickly tell me what is the time constant here? How do we go about it? What is the time constant here? So again, we need to Theveninize the circuit. We need to find RTH. L we know 1 millihenry. So your time constant would be L by RTH. What is RTH here? What is RTH here? Anyone please unmute and tell me. Anag, 15 by 14. Anag, can you please unmute yourself?
Yes, sir.
Why do you think so?
So 10 parallel with 5?
Why? Which 10 is parallel? Let me first remove this one, right?
Yes,
This
this
is
10.
open. Why it will be parallel?
Oh, current source is shorted, right? In
Is it
while
so?
doing
Sir, it is only 5.
Yes, it is only 5. You are right. Anag,
the current source is open.
yes, right.
Okay.
This is open.
Hmm.
So you will see only this resistance, right?
Yes.
So your RTH will be 5 ohm. So this kind of things may be slip of observation, but be very careful when solving these problems, right? So your time constant will be L is your 1 millihenry over 5 ohm. That is your 0.2 milliseconds, right? Is there any option? Yes, 0.2 millisecond. A is the right option. So moving on to the next problem. In this circuit, what is I3 0 plus? So T is equal to 0 plus, right? So what is T equal to 0 plus? Which circuit we should follow? This one, right? Okay, just let me do this. T equal to 0 plus. So let me just copy this. This is the circuit T equal to 0 plus, and we are supposed to find I3, right? And so first thing we need to find is what is IL at t equal to 0 plus. It should be t equal, one second. So IL t equal to 0 plus will be equal to, anyone? IL at t equal to 0 plus will be equal to 5 minus I3. No, that is fine. But what is the IL value? I need to find I3, right? I need to find I3 and I have 5. So I need to calculate I2, right? Sorry, IL, right? So I need to find out IL. IL at t equal to 0 plus will be IL at t equal to 0 minus. And what is IL equal to IL at t equal to 0 minus? IL at t equal to 0 minus IL, this is right, this is IL. IL at t equal to 0 minus. So Anag, why don't you tell me what will be IL at t equal to 0 minus 0, right? And this is the same funda that we have used in case of capacitance, right? Capacitor is getting discharged if there are any initial value. Similarly, inductor, the current will be discharged, the current will be reducing and current will become, sorry, the inductor case, the current will be flowing out and your magnetic flux will be draining and then your current becomes 0, right? So your IL becomes 0. Where did we go? So this is your 0. Now tell me how to simplify this circuit given this condition. We have this current source. So we have this current source, then this closed switch, this 1 ohm, this current is 0, right? That means we can consider it as open. And this is 5 ohm. I need to find out I3. This is 10 ohm, and this we just simply don't care about at this moment. So what is my I3? I3 is equal to 5 ampere, right? Your I3 is equal to 5 ampere, right? So D is the right option. I request all of you please to understand each step very carefully, right? You will forget, believe me, you will forget all these formulas after even one semester or so. So if you can capture these concepts very carefully, it will stay for lifetime. So please understand the steps very carefully. That is why I am breaking it down in so much steps. I can just solve it in one line also, but just looking at the circuit. But that is not the purpose, right? You need to understand each and every step very carefully. So please do that while when you solve your problem or assignments also. That is a request from my side. So moving on to uh, problem number 11. So we are asked what is I3 at t minus 1. So what is t minus 1? Let me go back to our circuit. So what is our t1? T1 is 0.3 millisecond, right? So t minus 1 means this case. Again, this circuit will use. In this will we use, and at t equal to This is your 0.3 millisecond, right? T1 is equal to 0.3 millisecond. What was the time constant, by the way? Did you find out? Yes. It was 2 millisecond, right? Your tau was 2 millisecond. So we can clearly see that again T is less than 5 tau. So we are in the transient regime. So how do we calculate this? How do we calculate? Did I derive the formula? Yes. This is the formula, right? This is 0. This is the formula, right? ILT. So your IL of T is equal to your IS 1 minus e raised to minus T by L by R, right? This is your formula. Then what about your IS? IS should be the Norton equivalent current, right? In this case, what is your Norton equivalent current? Can anyone tell me? For this circuit, what is the Norton equivalent current? By the way, how do you find the Norton equivalent current? Between these two terminals, right? How do you find out? Anyone? Please unmute and tell me, how do you find Norton equivalent current? Because ultimately I have to make this contraption, right? This contraption. This I know. So I need to find out this. This is nothing but your IN, Norton equivalent. This is nothing but your RN. So RN or RTH we have found out, right? This 5 ohms. So what is your Norton equivalent current for this contraption? Anag. Yes, right. It is 5 ampere because you just short it. This is not present. If it is shorted, it is not present. So current is just this 5 ampere flowing through this green branch, right? So your IS is 5 and 1 minus e raised to minus T is your 0.3. And what is this L by R? This is your 0.2, right? This is your current. So what is IL? IL at T equal to 0.3 millisecond. That would be 0.3, 0.2 alpha e raised to minus answer into 5. It will be your 3.88 ampere, right? If you calculate this, it will be simply 3.88 ampere. What they are asking us to find out, this current is 3.88 ampere. So what will be this current? I3. Your I3 will be nothing but 5 minus 3.88 ampere, right? Because this 5 ampere current is divided in this point and in this point, right? So this is nothing but 1.12 ampere. So your answer would be C. Okay. So let's move on to the next point. What would be I3 at T 1 plus? Here we have found out T1 minus, right? What is the difference? The difference is visible here, right? T1 plus is this point. T1 plus is this point, right? And T1 minus is this circuit. So at T1 plus, we need to consider this circuit. You will be considering this circuit. Then what is my initial condition here? My IL T1 minus. What was that? We just found out, right? It was this 3.88 ampere. 3.88 ampere, right? So can you tell me what is I3 now? I3 at T1 minus T1 plus, sorry. So it will not change the state, so it will remain T1 plus. What is I3 T1 plus? 0. Why? Oh, you are still off by some limit. Anak, please unmute and help me solve the problem.
Sir, it is in the transition state, so it is going to be discharging through the resistor.
Oh, right, you are right. But 3.88, are you sure
No,
about this
not
is the
3.88. It is less than
this?
that.
No, why it should be less than that? It is the same instance, right? This is T1 minus and this is T1 plus. It is the same instant. If you are switching means you are just here or here. So inductor will not change its state immediately, right? It has some resistances.
Yes.
So it is having some inertia, right? It will not change
Yes.
its value instantly. So this will remain same. So now my question is, if this branch current is 3.88 ampere, what is this branch current? You please notice that this is open circuited, right?
Yes.
So we do not have anything to do with this part.
Hmm.
Our circuit is just this right side.
Hmm.
So what is I3 if IL is 3.88? Basically, it is my this, right? This and this resistance. I am telling that this is 3.88 ampere. What is this current? Whatever is coming in your mind, you can speak out. We are just learning here, right? What is
So
this
initially,
current?
initially it will be 0. I3 will be 0. Because it will slowly discharge through the resistor.
No, that is fine. But we are talking about the same instance, right? T equal to 0.3 millisecond. Just 0.3 millisecond minus and 0.3 millisecond plus. The difference in between these 2 points is that my switch position has changed. So at t equal to 0.3 millisecond plus, my circuit is this only. See, if I give you some to use KCL in this loop, right?
Hmm.
What will be your answer? I3.
Minus 3.88.
Yes, right. It is just minus 3.88. It is not 3.88
Okay.
because this current is flowing in this way.
Hmm. Yes.
So A will be the right option, right? So see, this kind of storage elements, what happens actually is, as soon as at every instant of time, by the way, at every instant of time, your KCL and KVL is sacrosanct, right? It has to be valid. Even if it is at t equal to 0 minus or 0 plus, your KCL or KVL has to be valid. That is giving you the simplified circuit analysis. Otherwise, you will be solving all these transients and all. KCL, KVL will have to be valid. You just see this is a simple circuit, you ignore this part, and then you will find that this current is only flowing through this. So if this current is 3.88, so the opposite direction is just minus 3.88. It's just the convention, right? So moving on to the next problem. What is the time constant for the circuit for t greater than t1? Okay. What is the circuit for t greater than t1? This case, right? Now, please help me someone to solve this problem. How will I find the time constant? What are the steps? I just want to know either I am reaching to you or not. Anyone, just tell me how to solve this circuit and how to go about finding the time constant. Let me simplify that this is the circuit, then this part you can ignore. Your circuit becomes just this right side. So tell me what is the time constant? How do we go about it? No, I want to know the steps. Nag, I want to know the steps. You can unmute and tell.
Sir, this 5 by 1 L by R, right? 1 millihenry by 5.
No, that is right. But how? What are the steps? If a circuit is given to you, what do you do first?
Equivalent L and equivalent R. One L and circuit is uh, make only one R and one L.
Okay.
That is, and
If there
here
are if there are
both
more R, I can see there is one R here and one R here.
sir, the R2 is irrelevant.
Yes, you're right. So this what if I have more R, then what is the process?
Sir, combine them and Norton's equivalent.
Norton's resistance, right?
Yes, sir.
In this case, how do you find Norton's resistance?
Sir, in this case, no need to find Norton equivalent. Sir, only 5 ohm is
Okay, so
used in time constant.
between these two terminals, there is only 5 ohm, right? So there is no
Yes, sir.
source, so you do not need to null any source. So you
Yes, sir.
can just simply write it is 5 ohm, right? So your Rn is 5 ohm. Yes, you are right. I just wanted to check whether you are getting the steps or not, right? So this is your time constant will be L by R equivalent or Rn, that is 1 millihenry by 5 ohm, that is your 0.2 millisecond, right? So A is the right option. So moving on to next, they are asking us to find I3 at t equal to 0.4 millisecond. I3 at t equal to 0.4 millisecond. Again, we go back to the circuit cases. T equal to 0.4, where do we stand? Here, right? So we just copy this contraption and we just paste it here. Now, again, In this case, when t is greater than 0.3 millisecond, my time constant is 2 millisecond, right? But here, what is the time has elapsed? T elapsed is your 0.4 minus 0.3, right? It is 0.1 millisecond. Because at 0.3 millisecond, your switch has changed its position. From then onwards, we will start to find how the circuit is getting relaxed. So T elapsed is your 1 millisecond and your tau is 2 millisecond. So again, you can see that T is less than 5 tau. T is less than 5 tau. So it is in transient, right? We'll use transient IL of T is equal to IL of T. Okay, now there is an interesting thing. How do you find about the transient in this case? See, my equivalent circuit has become, this has become simply this, right? This is L, this is R. Can you simply tell me what is my ILT will be? Anyone? Keeping in mind that we have discussed this for a RC circuit with voltage source when it is 0, right? This condition. This condition, right? It is the same thing. This condition we have discussed when the voltage source is 0. So we are seeing the natural response of the circuit, how this RC circuit is behaving. What did we find? We found that my V is exponentially decaying, right? As we know that this is nothing but a dual of this circuit. This is nothing but dual of this circuit. Can we write this IL of 0 e to the power minus T by L by R? Can we write this? If we can write this, then tell me if your IL is then my IL 0 e raised to minus T by L by R, right? What is your IL 0 at this point or IL initial? What time stamp I should consider here? Please understand this problem that at t equal to 0.4 millisecond, I have been asked to find out the current I3. My approach is to find out what is the IL at t equal to 0.4. So see, when you disconnect this switch was connected to this at t equal to 0.3 minus, right? As soon as you convert it to this circuit starts to relax, right? So what is the initial IL for this? The initial IL for this will be at IL equals to t equal to 0.3 millisecond minus, right? From then onwards, this circuit will behave like this and this will start to relax. The circuit will start to relax. That means this will be your 0.3 millisecond minus, right? So what was IL at t equal to 0.3 millisecond minus? It was this, right? 3.88. So it is 3.88 e raised to minus, what is your t? T has elapsed 0.1 millisecond. This one divide by your time constant, right? So it would be 3.88 e raised to minus 0.5. So e raised to minus 0.5 into 3.88, it is 2.35 ampere, right? Now tell me, what is I3? Minus 2.8. No, I think you have you have typed it by mistake. Yeah, it should be minus 2.35 ampere. Yes, you have got the point of the last question. This proves that, right? So let me move on to this question number 15. It's minus 2.35. Did we have any option? Yes, B. B is the right option. So we'll move on to this question number 15. It was asked that in the circuit of Q9, okay, what is the energy lost in the inductor from this second to this second, right? So we need to find out the energy lost from 0.3 millisecond to 0.4 millisecond. Okay, what was my circuit in 0.3 millisecond? Right, equal to 0.3 minus millisecond to this is 1 millihenry, this is 5 ohm, and there is a resistance 10 ohm. Okay. Now, anyone please tell me where will this energy will be lost by the inductor? Where will this energy be lost in the inductor from the inductor between this timestamp to this timestamp? Resistance of 5 ohm, Anag. Okay, resistance of 5 ohm. How? What kind of energy it will be losing? And what kind of energy it is storing? Anak, please unmute yourself.
Yes, sir.
It
This
dissipate energy in the form of heat.
it will dissipate in the form of heat, right? We call it as joule heating. And what is the form of energy it is storing the energy in the inductor?
Magnetic, sir.
Right, right. So we see that energy conservation is always applicable in the nature, right? If somebody is losing some energy, it should be going into some other form of energy, right? So here we are seeing that magnetic energy is being dissipated as a joule heating. So how will you calculate the how much energy is lost? There are two ways. Either you calculate how much energy the inductor is losing, or you calculate how much energy the current resistance is dissipating, right? In both ways, you will get the same answer. So let me do it in the inductor way.
Half Li square.
So, right, the stored energy at inductor at t equal to 0.3 millisecond is E1, say, half Li square. As you have rightly said, it's a very simple proof. You can just do it. Half Li square means half into what is your L? 1 millihenry into I square, right? What was your I? It is 3.88 at this instant. Okay. And remained means stored energy at inductor at t equal to 0.4 millisecond is half is your E2 is half 1 millihenry into your this is 2.35 square, right? So your delta E is E1 minus E2 half into 1 millihenry into 3.88 square minus 2.35 square, right? This much ampere square. So ampere square into milliwatt will give you millijoule, right? And then 3.88 square minus 2.35 square is this divided by 2. So you are having a loss of 4.76 millijoule, right? So this is the right option. So I think the problems are done for today. Here we stop. And now use this 10 minutes. If you have any question or any doubt regarding this session or the concepts I have covered this week or last week, you can please ask. You can unmute yourself, tell your name and ask.
Sir, what is the purpose of energy identifying the energy storing elements?
Purpose of identifying the energy storing element.
Hmm.
Okay,
Starting with that.
okay. Let me put it in this way. Suppose you are aware about MOSFETs.
Yes.
Okay, in MOSFETs, if you see, if you look at to the gate of the MOSFET, it is a capacitive completely, right? The
Yes.
gate to body capacitance, it is a
Yes.
CGG, it is a completely capacitive network, right?
Yes.
Suppose you are having an antenna. Your antenna is receiving a signal. You can anyhow make your antenna as a resistance and a voltage source in series, and you have to match your impedance through the capacitive network, right? For the
Hmm.
maximum power transfer to occur.
Hmm.
So in those type of calculations, you see your capacitance is not a energy dissipating element, right?
Hmm.
And your resistance is an energy dissipating element. So to match the resistance, you need to find out how good your impedance matching is. So you need to somehow put out of this you need to ensure that how this capacitance and capacitance are storing the energy and all to get the maximum power transfer. That is one case you can tell. Another way, this mobile chargers, you know, the mobile cells,
Hmm.
batteries. These batteries, how they store the charge. There are so many technologies, right? You might have heard about supercapacitors also.
Hmm.
So in those cases, basically you take it in this way that capacitors are used to store energy in form of charge, right? Now, so that it can be used at a later time. And also
Okay.
you see that if any two wire there are current flowing, right? They any two metallic wire, if there are any potential difference, so there will be a capacitance in between, right?
Hmm.
So in case of electrical circuits and electronic circuits, you will find these capacitances everywhere. We call these parasitic capacitances, and it is very hard to deal with. So to know the dynamics of the circuit and to know how these capacitors are behaving, you need to know this kind of stuffs. How to calculate the order of the circuits, how much energy capacitor is storing, and how it is dissipating to some. See, anywhere the current is traveling, it will be facing some resistance, and anywhere there are two parallel conductors, it will have some capacitance. Take it assured. Now, in terms of how you operate the frequencies, what is your operating frequency? It will have different attributes. In high frequency, these parasitic capacitances are very dangerous, you know, because it is having a low impedance, so it is draining the current.
Hmm.
So, understanding of capacitance charge storage is very important. So this
Okay.
is case of this. energy storage element for capacitor, and for inductor, you know, RF chokes, right? Not RF chokes, any chokes you can think. It is a inductor, right? It stores energy. Choke is nothing but a coil, that is inductor. So there comes this handy. How you see, this is the course of basic electronics, right? So I am explaining the electronics part. In electrical also, there are capacitor banks are used in substations also. So these analysis, you may think that these are very trivial analysis, but this will come very handy even you are in industry, you are in academia, you are doing higher studies. This analysis will be everywhere, you know. Even in if you are serving in, you will be pursuing IES and all in railways. They use this basic analysis. You should be very thorough and understand every circuitry very well. And so I was requesting you that to go through the steps very carefully, right?
Okay.
So any more questions? Okay, then if there are no question,
Sir,
yes,
sir, I have a basic question. Sir, in
yes,
RC
please.
circuit,
Mm-hmm.
how you write VC is equal to VC minus VS by RC? Sir, elementary question, but I am not getting it.
Okay. Just let me go through that point, right? In RC circuit, this one, right? Oh, no. Which one you are talking about?
RC circuit with a voltage source.
Okay. This one.
Yes, sir.
Which part
Um,
do you have any problem? Do you have the problem?
VC is equal to VC minus VS by RC.
VC is equal to which line?
Mm. Pink above the pink line.
Okay, this one.
Yes, sir.
Oh, this one, right? This one, how it is coming, you know. This, if I go from this line to this line, then what is happening? Your Vs minus Vc of t is equal to Rc dVc dt, right? Then you can just take this on the other side.
Yes, sir. Divided by RC.
Yes, that divide. Do you get it? Plus Vct minus Vs. Did you get it?
Yes, sir.
Okay.
Yes, sir. Yes,
Any
sir.
okay. Any other doubt?
Sir, I think I had misunderstood. I think you write written VC is equal to VC minus VS by RC.
Oh, okay. Now you are clear, right?
Yes, sir. Yes, sir.
Okay, no issue. No issue. Okay, fine. Then let us stop the call here and we'll meet in sharp next week 3 p.m., right? Okay. Thank you.